But we have a good meeting for you tonight. We've got some interesting stuff that we're going to be talking about. We've got a couple of good talks. We've got a whole boatload of interesting observations. It's really good to see you guys getting out there, because you know what? I was feeling pretty lonely over the winter, thinking I was the only lunatic getting out there taking images. So it's we've got some guys playing catch up there with some really beautiful stuff. So I think you won't be disappointed. All right. What do we got? So this is our agenda for tonight. Al's going to give us his usual astronomy news update. Some good news, some bad news going on there. I see Gary made it, so we've got Ottawa skies happening. Bob is going to give us an interesting talk on auto guiding and a rather innovative way he's found to do his guiding there. So I'm looking forward to hearing that. We'll have our break and our door prizes. We've got a number of books to give away. Also, there's some magazines up at the front there. Those are giveaways. Have a look at them at the break there if you're interested. They're yours. Also, on the side by the swap table, you notice that there are some circular objects there. Those are drum skins. Those are drum skins donated for modification use. And so if you're interested in doing a solar filter or perhaps even a Dobsonian, check them out. They're free. Okay, so have a look and see if you can use them. You can haul them away. At least one, anyway. Okay, then Tim is going to talk to us about Hawaii and what's happening with the Canada-France-Hawaii telescope. We've got our observations section. If we have time, we'll see how we go. We've got a fairly good agenda tonight. I'm going to give you just a little bit of I want to play something of the tour video of the International Space Station, because what I'm planning to do next month, I'm working on a talk that will summarize the work that Chris Hadfield did while he was up on the ISS for 6 months there, and so I thought this might be a nice prelude, show you, sort of give you a tour of just how big the station is, and it's quite a nice piece of work there. You get a tour of basically the entire facility, which is a lot bigger than you think it is when you get a tour like that going through it. And then Eric is going to talk to us a little bit about public outreach. So without further ado, I think we should roll. We've got one member in the news, and I love this picture. There. Yes. Yeah, Simon. Is Simon here tonight? No? Oh, man. I guess he's still looking for his razor, eh? Yeah. Man, he's looking wild. He looks like he's been up on some geological site for the last 3 months there. But good on him. He won this medal from the J. Willis Ambrose Medal presented by the Geological Association of Canada. And as you can read, it's awarded to an individual for sustained and dedicated services to the earth sciences community. And for those of you that have listened to Simon speak, I think you will probably agree with me that it is well deserved. So congratulations to Simon. And I think we'll award him an ancillary prize of a Bic razor there for the next meeting there. What do you think? Shall we do that? All right. Love that. I love that picture.
These talks are on the web.
Yes, that's right. They're on the web now? Oh, okay. That's good to know. I wasn't aware of that. So if you've missed some of Simon's talks, how many have we got up there?
I'll get 5 or 6.
Awesome. Well worth checking out. As you know, he's a pretty dynamic speaker there, and I always love listening to his presentations there. So good stuff. It's up on our Ottawa RASC site.
On the front page, just click on it from there.
Wonderful. Thank you. All right. Mr. Boyle, I did see you.
Okay, well, good evening, folks, and sorry for the accommodations. I can't wait to see the broom closet next month. But no, the emails will be sent out this month this week for sure. Okay, so let's roll up beautiful beam footage. The first objects in the western sky how many people have seen the trio of planets at the end of May? Yeah, that was something for sure. Well, now we're going to see just 2 planets. In fact, on the 20th, Venus is just like a horse race. We have Mercury is coming up from behind the sun, same as Venus, but now Mercury is beginning to stall as it begins to round, and it's actually going to become stationary. Mercury, and once Mercury does that, then Venus will bypass. And Venus will be moving up further and further. So Mercury will be at its greatest height on the 18th at 24 degrees. Next slide. The International Space Station is passing over Ottawa, of course, pass over major cities all over the world. But for us here in Ottawa, if you can check over here on the 16th, pretty well the brightest, minus 3.4. And Jupiter itself is minus 2.8. So it is extremely bright. And what really gives the brightness is the high. It's almost directly overhead. So on the 16th, at just after 11 p.m., look straight up and you'll see it. Next slide. So in the southern sky, we see Corvus, Spica, and Saturn, our main planet of the night. Of course, like I said, Venus and Mercury are very low, but Venus will be coming up. But to get some kind of detail, Saturn is always a favorite. And then, of course, we have the Milky Way with Scorpius. Next slide. So once you look at Saturn, who has seen Saturn in a telescope? And have you seen all 7 moons? How many have seen all 7 moons? 6 moons. 5. 4. 3. Excellent. Good. So on a good night with some, well, large aperture telescopes, about maybe 12-inch or so, you'll be able to see all 7 moons. Very, very dramatic. So check the Observer's Handbook if you do have a copy on the various ephemeruses of when the satellites are in various positions.
Not to scale, though, right?
Not to scale. No, definitely not. Definitely not. Next slide, please. Yep, so here we have Corvus again. And just up here, we have a beautiful galaxy, M104, the Sombrero. And next we'll see a close-up of that. So pretty well what we take as Corvus to Crow, we move up to these 3 stars, and then you get 3 more stars that really point to the galaxy. And once you, again, depending on the size of your telescope, the larger the mirror, the more light gathering power, just like CCs on a motorcycle, the more CCs, the more power, we'll see a beautiful galaxy. Next slide, please. And of course, this is, of course, the Hubble shot, but you will not see it this good, but still you will see the beautiful dark line, the dust lane in the galaxy, and it's a true classic edge-on galaxy. Very, very dramatic. Next slide. And on the 20th, in fact, on the morning of the 20th, at 4 minutes after midnight, on the 21st, for here in Eastern Canada, which means as you go further west, it's actually the night of the 20th. So when people argue, oh, summer is the 20th, no, the 21st, it depends what time zone on this one you really live in. And this is when the sun is at the very, very top of the ecliptic, and solstice actually means sun stands still. So we had the summer solstice in the summertime and winter solstice in the winter, of course, and that's when the sun is at the highest or lowest on the ecliptic, which means now the longest days pretty well the next week or so. And now the days become shorter, the nights get longer for us, but majority of the population don't like shorter days. I don't know why, but astronomers do. Next slide, please. And just our rundown of your favorite planet. Now, Jupiter is lost in the solar glare. It actually moves behind the sun on the 19th. Okay, next slide. And for people that follow the moon, we had I don't name them, the strawberry moon is on the 23rd. And in fact, it's the closest perigee to Earth for the whole year. Next slide. So who were here for the David Levy talk last week? Excellent. Well, I'm glad we didn't have the conference room. I'm glad we had the auditorium for that one. David gave us a great talk. He's a personal friend of mine since 1976. Actually stayed at my place. He had a pretty busy day. Came in by train at about 3 in the afternoon. Had to rush him off to CBC Studios for a 4 o'clock appointment. Then we, next slide please. Then we had supper. Also met with some of our elite members, Barry Matthew over here. So David really mingled amongst the audience, and whoever wanted to approach him, he's very approachable for sure. Next slide. And gave a great talk on just his adventures as a night watchman. David has discovered or co-discovered 23 comets in his career. Still looking for comets, even though it's almost impossible because of all the photographic telescopes out there now. But he does use photographic means, but does observe too with the eye. And also, David even won an Emmy back in 1991 for 3 minutes to impact on Discovery Channel. He didn't even know that he won it until he got the phone call saying, "We got an Emmy." So it's in his office. He didn't bring it. I asked him to bring it, but he didn't. But it's in his office back in Tucson, Arizona. And funny story, when journalists or people come to visit, they look at, is that an Emmy? Oh yeah, it's an Emmy. But glad you enjoyed it, and it was great to see David. David is actually doing a tour of 7 RASC centers in Ontario and in Quebec. Next slide. So we like the fact they thanked the many volunteers that night for manning the front table, of course here at the booth, and behind the scenes. Really, really appreciate it. Round of applause for these people. Excellent, thanks. And next slide, please. And here it comes, the volunteers needed. As you know, we always have the Carp Star parties at a great location just near the Diefenbunker in the western part of, of Ottawa. Unfortunately, we do not have an outreach coordinator for the Star parties. I've gotten the ball underway. I'm going to fill out the forms, get the insurance. We have some dates planned. So the first date that I have planned is July 6th. That's tentative for now, but that's one day after our meeting. Our meeting is July 5th next month, so I just want to announce it now. And on the website, we'll be populated with the various dates. But we do need someone to head the Star Party, Star parties from now till October. So if you can see me during the break, if you can just help organize, get scopes together. It's not a lot of work, but it's great to have one person in charge. It'd be great. Appreciate it. No stampedes, no stampedes. And I think that's it. That's it. We'll see you later with the gallery. Thanks, folks.
Well, thanks, Gary. Okay, next up on deck is Mr. Scott with his astronomy news update.
So, I've put together 3 news items for tonight because I heard we were short on material, but apparently not. So the first one, this is a bright dwarf galaxy in the Virgo cluster. It's been imaged by the GALEX ultraviolet satellite. It's IC3418, and it's been imaged trailing bright fireballs and is the first clear example of a galaxy in the act of dying. Astronomers believe that we are observing a critical stage in the transformation of what was once a lively, gas-rich dwarf irregular galaxy into a gas-poor dwarf elliptical galaxy with no more new stars being formed. The image here, you can see X-ray emission is in false color, and this is the dwarf galaxy here with its trail of fireballs. This is ultraviolet from the GALEX, magnified 10 times with respect to the rest of the image, just to show it up, because otherwise it wouldn't look like much. Star formation is the essence of galactic vitality, and many of the universe's known galaxies are active star factories, but due to gas depletion, many others have stopped making stars, rendering them in a sense lifeless. This galaxy is now all but totally out of gas. Researchers used the WIN 3.5 meter telescope in Arizona and the twin Keck 10 meter telescopes in Hawaii and performed both optical imaging and spectroscopy on the galaxy. The spectral signature of the core of this galaxy suggests it stopped making stars between 200 and 300 million years ago, but its distinctive fireball-dotted tail shows evidence of recent star formation within the last few million years or less, they estimate. The depletion of the core and the generation of the fireballs are probably the result of the process that's killing the galaxy, what astronomers call ram pressure stripping. In this process, as the galaxy orbits through the Virgo cluster and plunges deeper into the cluster through the hot gas that's emitting the X-rays, it basically piles up a shock wave from this gas, and the enormous shock wave strips the tenuous gas clouds from the galaxy's weak gravitational hold. The stars themselves in the galaxy have too much momentum to be affected by the gas at all. The ram pressure also causes the leading edge of the gas clouds that are stripped to collapse and form bright young stars and leave behind a stream of fireballs. So quite an interesting discovery. This is an interesting one, and continuing with the theme of death. Like a CSI unit, a team of astronomers at universities worldwide have been digging around in the innards of dead stars, collecting evidence on how they died. One of the dead stars actually ate part of its neighbor. WET is an acronym standing for the Whole Earth Telescope. It's a worldwide network of major observatories with its command center at the University of Delaware. And what it does is it periodically focuses on stars of scientific interests that it wants to have long-term observations of continuously. So these stars are handed off from observatory to observatory as the Earth turns to allow them to basically monitor their light curves continuously. Canada's CFHT is one of those telescopes in the WET cluster. With a marathon 2-month-plus observing campaign set to finish on June 10th, which is the longest in WET's history, the collaboration expects to yield new insights into the astrophysics of white dwarfs, which are dense stars that have burnt up their nuclear fuel and are now just very dense and cooling. The team, what they want to do is understand the physics of this dense white dwarf star matter, which is, you know, there's nowhere else in the universe really that you get that sort of matter. White dwarfs are just a little bit not quite mass enough to collapse in a supernova into a neutron star. So they still have what you would consider normal matter, electrons and neutrons and protons. The team's primary target, the low-mass, extremely low-mass white dwarf known as WDJ1518, was once part of a 2-star binary system before it ate its companion, or at least part of it. It is now in a 14-hour orbit around something that is probably another white dwarf or a brown dwarf. The second target star of this campaign, GD358, also waxes and wanes in brightness as the star pulsates, just as many other white dwarfs do. Astronomers record changes in the white dwarf's luminosity in graphs of light intensity over time called light curves. These graphs typically show regularly repeating sinusoidal waves, just nice up-down oscillations. However, nearly 20 years ago in August 1996, GD358 committed what astronomers refer to as a whoopsie, which was a period of extreme oscillations in its light curve, mimicking a huge roller coaster gone wild. After 2 days of giant peaks and dips in its brightness, the star stopped pulsating for a month. So what astronomers are doing is trying to find out what might be going on in these stars. Did it get hit by an asteroid? What could cause this extremely dense matter to pulsate like that in such a bell-ringing fashion and then just to suddenly stop? So hopefully...
What kind of periodicity and amplitude in brightness?
I'm not exactly sure what the periodicity is or the amplitude. I don't have that data with me, but what they're going to do is they're going to take the 200 gigabytes of image data that they've collected over this period and stitch it all together. And so it must be long enough that they can, you know, hand it off between telescopes. I don't think it's extremely fast. I think it's just something that's on the period that could be measured reasonably easily. The last item. The successful Kepler transit hunting spacecraft has lost 2 of its 4 momentum wheels, which keep it stabilized and pointing on its target field of space, as you can see there, towards the center of the Milky Way. It's no longer now able to stabilize on its targets, needing 3 axes to be able to give it the sort of stability that it needs to monitor these targets for planetary transits. Although the mission did meet its scientific goals and its lifetime goals, it still had sufficient fuel to continue to 2019. Unfortunately, this appears unlikely to be the case. For the past 4 years, the $600 million telescope has been a planet detector with a 1-meter wide lens monitoring thousands of stars, monitoring photometry or brightness of these stars, looking for subtle dips in their brightness, which indicate that a planet has moved across the star. And what they do is they look for periodic eclipses, basically, that tell them what the size of the planet is and the size of its orbit is. Kepler's first 22 months of data have found planets that are quite obvious. Most are in the wrong neighborhood to sustain life as we know it, either too close or too far away from their suns, or they're big gas giants. The Kepler science team, however, still has 2 years of science data that they haven't combed through yet. So there's more likely to be announcements coming over the next few years as they comb through it, supplementing the 2 Earth-like planets they've announced so far. The software that they use to analyze the reams of data that the spacecraft provides are continually being upgraded to try and tease out more information out of the noise and distinguish these planetary obscurations from stellar pulsations and any number of other potential solar flare activity or things that could, or astrostar flares that could actually masquerade as a potential planet. And now they aren't going to be able to go back and follow up on these with the Kepler Space Telescope. So good news in the future, though. Due to Kepler's success, there are 2 new planet hunting missions on the drawing board. So hopefully those can get funded and get launched and follow up, where Kepler's really changed our view of the universe. From the data that we found from Kepler, we now know that planets are prolific, and most stars in the universe have these planets, which we didn't know 10 years ago. This is a whole new set of data that basically affects one of the numbers in the Drake equation and actually starts to nail it down a little bit. So it's been a good mission. It met its goals, but unfortunately it looks like it may not be salvageable. They're going to try to see if they can stabilize it using some of the other less accurate tools like the torque rods, the magnetic torquing that they may be able to use, but it doesn't look like it's going to be able to continue. So that's a little bit unfortunate. So thank you.
All right. Thank you, Al. Mr. Olson, come talk to us about your Canadian Tire telescope.
Well, this is certainly the most flattering light that I've ever been in. Did I remind you of Boris Karloff? Jeez. My interest in astronomy is imaging rather than looking through a telescope. I will look through one if I have to. If somebody has a nice one set up, I will do that. So imaging, and it's very difficult to image for very long exposures if you don't guide. Chris was looking at this slide, and he noticed my sign right here and was a little bit interested. And this is a sign that was given to me by my wife. And she tolerates my hobby, and I wouldn't want to say encourages it, but certainly tolerates it. And she tolerates enough even to come tonight, and which bores most people out of their minds. I image with a dedicated CCD camera. It's really meant for astronomy and nothing else. It's a Starlight camera. The fins that you see on it are for cooling. I cool my camera down to 30 degrees below the temperature that the air is. That reduces thermal noise in long exposure images. You take a picture of Aunt Matilda at Christmas, you know it's 1,000th of a second. And I'm taking images that are 4 minutes at the minimum and hours at the longest, so noise matters to me. The chip is pretty small. It's pretty small. It's 9 millimeters by 7 millimeters, 1,400 pixels across by 1,000 pixels deep. And that makes the individual pixels pretty small. They are 6.45 micrometers, or to say it another way, 6/1000ths of a millimeter. So they are pretty small. If you look at it this way, the matrix of the chip that I'm imaging on, 6/1000ths of a millimeter are the individual pixels. So that was basically the smallest thing. That'd be the resolution of my images. Now, what you're looking at right here is a graph of a star image. And as you can see, it goes, the height is here, and that's how bright it is. And across the bottom is the actual position. And you can see that where does it end over here? It's hard to tell. So what they have arbitrarily done is they've gone halfway up, half max, from there to there, halfway up, and they measure that width right there. And they call that the full width half maximum of a star image on my camera, and they are astonishingly similar in all these stars, given that it's not a really bright star that's blown out my image. But typically on my camera, that would be 2 or 3 pixels across. And what does that depend upon? That depends upon the quality of my optics. It depends on the focal length of my optics. It depends on how stable the air is. And I tend to live under the jet stream, so it's not really stable. So there's no point in having all kinds of pixels in here. That's the resolution of a star. There's no point in having like 1,000 pixels in there. But what does this mean here now for guiding? Well, it's 2 or 3 pixels across, And if that star image moves more than a pixel, I would even suggest if it moved more than 1/6 of a pixel, you'd see it in the images. That means that when I'm taking an image, I've got to put this thing on the same spot on my camera within 1/1000th of a millimeter. And if it moves, you're going to see it in my images. You can imagine that's a pretty monstrous technical thing to be able to keep an image that stable. And mechanically, it's almost impossible. What I have to do is I have to guide my camera to stay on the same pixel. And there's all kinds of ways of doing that. One of the cleverest ways, I think, is to have a camera with 2 sensors in it. I'll take the picture on this one, and I'll put a star image on this one, and I'll just keep the star image on the same pixel for the whole exposure. And I do that using software. So if the pixel, the star image moves a little bit, my computer signal is sent to my telescope to move it back and center up that pixel again. The mathematics allows me to, I believe, get to about 1/100th of a pixel. Obviously, my telescope is not accurate enough to move that, but it can easily move 1/10 of a pixel and keep a star image centered up pretty well. And if it moves more than about 1/5 of a pixel or 1/6 of a pixel, it'll show up. Now, a company called SBIG, in Santa Barbara, they patented this method of having two chips in a camera. So if you don't use a Santa Barbara camera, you can't use this method. Another method is to use something called a pick-off mirror. And so this little mirror right here picks off some of the light, sends it up to the guide camera up here. And you have to keep this, obviously this little pick-off mirrors can't be in the image, otherwise you'll have a shadow. It has to be above the image. And that looks like this. So the mirror picks a little bit of the light off, goes up into the camera, keeps it on 1 pixel, and will keep everything together for quite a while. Here's the camera that's taking the image over here. There are some problems with this system. This pick-off mirror can't be very big. And clearly, if you have this system, this thing can't be too big either because there's no room for it in the camera. So that's a pretty small little sensor that we have there. So that means small field of view, and it's really easy to take a picture and there'll be no stars that you can guide on that imaging, on that guiding chip. That's a serious problem. Another serious problem they have, even if there is a guide star, and it's a dim one, as soon as you roll filters in front of it, it's going to dim enough that you won't be able to guide on it. And I use a monochrome camera, and I put red, green, and blue filters in front of that to get my color images. So this matters to me. All right, what's another method? Well, slap a telescope on top of the one you're imaging with and put your guide camera on that. So here's your guide camera, here's your imaging camera, and as long as those two telescopes point in the same direction, you'll be able to guide. And these are typically low focal length telescopes, these guide ones, and they have a big chunk of the sky. You can have a big chip on them. It's a great idea. But if you look at how, see this thing right here, this part up there? That's really pretty rickety. Those tongs that hold the guide scope, there's no way they're going to hold it within 1,000th of a millimeter. Not a chance. It's going to wander all over the sky. So when I was using this method, I used solid rings. These felt rings grab the guide camera more securely. It manages to keep them pointing in the same direction. And I was able to guide fairly well with this system. My guide camera kept right on the star the whole time. Problem wasn't my guide camera, it was my telescope. I use a Schmidt-Cassegrain telescope, and this mirror, we focus by moving it back and forth along here. And there's no way that that's going to move back and forth and not change where my image is. So although my guide camera could guide on a star, my main camera couldn't stay on the same field of view. And so I would get some movement of my images. Also, this telescope tube right here is either thin aluminum or thin carbon fiber, and it flexes a little bit. And when the telescope and the guide scope don't point in the same direction, we call that, and they change, we call that differential flexure. And that's a serious problem. So here's an example of a single 4-minute exposure. It's pretty noisy already, it wasn't processed, but if you look carefully at a star, and then you magnify that star, you can see that it moved. And it moved in this particular case, obviously, about 6 thousandths of a millimeter. That's how much it moved, and it showed up with this little streak instead of a round star. If I processed a whole bunch of these images, it would look terrible. That's not satisfactory guiding. And as a matter of fact, I was having a bad night this night, and here's the stars. As you can see, each one of them moved over a little bit. There's 6 stars there, and it moved each time about 6 1,000th of a millimeter. And the image is useless. All right. What's a possible other method of doing this? If you look at the spectral response of this happens to be my camera, this green line right there is the dividing line between infrared on that way, and this is visible light over here. And the black line is my camera. You can see that my camera is fairly sensitive in infrared. And so if I could somehow split the light into infrared and visible, I could guide on the infrared and image in the visible. Turns out that it's called on-axis guiding if you do that. And the piece of equipment you use looks like this. That doesn't really help you much, does it? Well, this is how it works. We have a beam splitter mirror right here, which reflects visible light and passes infrared. And so over here, I put my guide camera, and I guide on that image. Up here, I take the visible light, and I image with it. I can't image with infrared anyway because it gives me false colors. The infrared, we can't see it, and if you put it in an image, you end up with weird images. So I can't use that light anyway. Let's see if I can guide on it. Okay. What happens? Well, my wife is here today. This is all the junk that I hang on the back of my telescope to use this method. As was mentioned, this is not a trivial amount of stuff. And this is a close-up of the same amount of gear. And here it is with some labels and light paths on it. This is my focuser. It moves all this stuff back and forth to get a nice sharp image. The light comes down here, hits that beam splitter mirror. The visible light goes up here to my imaging camera, and this is the filter wheel that I use to take my red, green, and blue pictures with. The light passes right through this beam splitter, which is right in here, into my guide camera, and I guide on that image. Now, I want you just to take a look at the side. This is my guide camera right here. Here's the guide camera that I was using before. It's the size of an eyepiece. Little tiny pathetic thing. It's 8-bit and it's got a real small chip and it's not very sensitive to infrared. So when I tried to use this, I had to switch to one of my old imaging cameras to make it work. This was not sensitive. The little one was not sensitive enough to use. And this is what happens when you have a guider that's chasing after a non-existent star. You thought the other image was useless. This is even less useful. All right, now just while I have this picture up, I had a problem with my telescope at the same time. Can you see my nice carbon fiber tube? I bought that and installed it myself. And I'm embarrassed to admit that I did it because I thought it looked cool. All right, but I rationalized it by saying it doesn't expand with heat and cold, expand and contract with heat and cold as much as does aluminum. Aluminum expands and contracts like crazy. Carbon fiber is not too bad. It's pretty stable. And so then after I did that, I very cleverly took, I took my front cell right here, which is my corrector plate, and my mirror cell back here, and I bolted a great big aluminum plate to it to mount my telescope. And then on the top, I bolted another great big aluminum plate to mount my other stuff on top of that. So I had this non-expanding carbon tube, and I bolted 2 great big pieces of expanding aluminum to it. A stroke of engineering genius. Needless to say, the bolts on the aluminum were stronger than the bolts on the carbon fiber, and it actually worked the bolts loose. And my telescope was actually flopping around loose, which made the imaging even better. So what I did was I had to make a change, and I replaced instead of bolting it to this, I put a ring around it there and another ring around here instead of bolting it to the bottom part. So now my telescope is floating between these rings, and these rings have felt between this ring and the scope, so the carbon fiber can actually expand and contract and slip a little bit in that, and that stopped that problem. And I tightened up the bolts. By the way, when you loosen up your bolts on your telescope, your collimation goes to hell, and that was fun too. All right, next problem I had was, this is my telescope pointing upwards, and you know, because I'm imaging in the sky, it often points upwards. This is all the stuff that I have hanging on my focuser right here. And I was doing this, it was about minus 20 outside, may have contributed to the problem. My focuser wouldn't move this pile of junk up and down, so I couldn't focus my telescope. I helped it along with a couple of springs. I just put some bolts here and here on the sliding tube, and I put them up here, and these springs they're strong. They're probably holding up 5 or 6 pounds each, and they took the load from the focuser, which allowed it to now function when it was the scope was vertical. And here you can see them now being used, holding up all the stuff below them. The other problem I had was I have so much stuff hanging off the back of my telescope that I couldn't balance my telescope, and I had to bolt a brass weight to the front half of it. So when I did that, then I could get balance. All right. How well did it work? Well, these images are not really well processed, and they're not really long duration. But if you look at the stars, you will see that they are absolutely round. And as I use a cutoff now, 1/10 of a pixel is my cutoff. If an image is out of round by more than 1/10 of a pixel, it's discarded. And I'm not discarding any images at all. I'm getting great guiding out of this system. That was the first image I took, by the way, with my new system. This is the Whale Galaxy. And again, not long exposure, but the stars are nice and round. This is M65, and in March there was a supernova, which is what I was really looking for. Showed up really clearly in the image, and it's round.
How long are your subs?
Subs are 4 minutes. Yeah.
Typically?
It shows you how you get stuck in your ways. 4 minutes was all I could image before, because my image was removed. If I was much longer than that, I can now image for 10 minutes probably pretty safely. And I just haven't changed my setup to do that. There's no reason not to image for longer subs. Although if you screw up a 10-minute sub, you've lost 2.5 times as much data. This one here is a kind of a horrible picture, but when I was in Texas at the Texas Star Party, the guy next to me with an 18-inch job was looking at this. And it showed up as kind of 2 fuzzy blobs. And I thought I'd like to see, this is a 20-minute exposure. And I was sort of interested in the NGC 4567. It was a kind of a neat number. And the Siamese twins, it's kind of an interesting object. I might be interested in imaging that longer to get a better image. And again, in Texas, this is M17, and turned out pretty nice. Again, about an hour exposure. And again, in Texas, these are all from Texas. I just got back from Texas at the Texas Star Party. This is a Trifid, and again, I hardly discarded any images at all due to bad guiding. So the guiding method is not too bad. All right, what are the problems? First of all, much heavier load on the focuser, which is a problem, which is a serious problem. You need a bright star a bright IR star, infrared star, in the field of view. And since I've been doing this, it started in the beginning of this year in January. I have twice been on a sort of a blank field, and there hasn't been a star bright enough to guide on. The guider has a kind of way to move the guider off to the side a bit. And so I just push the guider off to the side, and there's always been a star there. But it's a nuisance. I do automated imaging some, and I really like for a guide star to be there. So twice out of maybe 30 times, there's not been one. And it's expensive. If my wife wasn't here, I'd tell you how expensive. You can expect to lose about $1,000 when you're all done for that beam splitter. It's not a cheap piece of kit. What are the advantages? A fabulous wide field. It allows you to do automated imaging. You know, the software will just find a guide image and start working away on it. There's no differential flexure at all. It's obviously the same beam path, so it can't be any flexure. And so far, I'm getting great guiding. Thank you very much.
Great. You don't need the lights.
Nope.
Okay.
Nope.
Super.
Hi, everyone. May 15th, I did an outreach for the RASC. Actually, it was a presentation on impact craters, but I did it under the banner of the RASC, and it was at my old high school, actually, Philman Wright High School. It's also a junior high school, and my son attends there. So the science teacher invited me to do an all-day, 5 classes. It was fantastic. I loved it. I'd never done that long a stretch before. And I focused on impact craters, asteroids. I highlighted the recent impact in Russia. And I really encourage the students to take an approach to science, that science is not just about studying to get a job. Science is a lifelong experience. And that through science, by learning, you know, how to do things scientifically, you actually gain a new sense. You know, you don't sight, seeing, hearing, touch. Science to me is kind of like an extra sense that allows you to explore the universe in a way that your natural senses can't. And so I really focused on now with the students to let them know that even if they don't pursue a scientific career, science should be part of their life. It'll reward them very much. And also I should mention that Chuck O'Dell joined me for one of those talks, and he presented you know, he has a different way of presenting things, maybe more forensic, more in-depth than I can do, because he's actually my teacher on impact craters and a lot of other stuff. And that, so I wanted to share that with you and let you know that science is a happening thing at that school, and I was glad to be part of it. Did anyone have any questions? No? Okay. Thank you.
All right. So Tim is going to talk to us about what's happening with the Canada-France-Hawaii telescope. There you go, sir.
Thank you kindly.
Watch the cables.
Yep. Oh yeah, you would adjust this for tall people.
Sorry.
Okay. Well, I've long had a really soft spot for the Canada-France-Hawaii telescope. These guys still do incredible world-class work with what nowadays is a pretty tiny telescope. So when I had a chance to look over the place, as luck would have it 1 year ago today actually, one of the things I was really interested in doing was being able to learn a little bit about how they managed to pull off staying relevant when you've got huge telescopes coming around. And it's really kind of fascinating to see how they've pulled it off. Thought I'd give you a look back in a bit of ancient history, just to put the stuff in perspective a bit. In the early 1960s, there was nothing up there. Gerard Kuiper, the same guy who brought you the Kuiper Belt, actually set up an observatory on this hill right here, probably at the end of the road. I'm not sure where it was. I never could find out, to test how good the conditions were in Mauna Kea. What he ended up discovering was, in his words, this is probably the best, I repeat, the best location in the world for astronomical observation. That's, of course, debatable, but the seeing on the summit of Mauna Kea is most likely the best anywhere, even better than the Atacama. They have more usable days per year, but the seeing up there is incredible. Just the confluence of sea breeze and location, everything conspires to give it an unbelievably still air up there. 1968, the United States Air Force actually set up a couple of observatories. You can see one here and one here. For satellite tracking and other things. They weren't too happy with the performance of it, but they gave these to the University of Hawaii. The University of Hawaii was granted control over the astronomy precinct up there, which actually annoyed Kuiper to incredible lengths because they wanted the established, respectable universities to get control of it. And at that point, University of Hawaii was basically backwoods U. So, in 1970, the University of Hawaii opened their 2.2 meter telescope, the one here that looks ridiculously like either a light switch or a coffee dispenser. That's actually a crane. The original method was they'd hoist the illuminization chamber up through that crane to re-illuminize the mirror. And into that world, we had the Canada-France-Hawaii telescope coming. So here we've got what was up there after the Canada-France-Hawaii telescope went in 1979. It was quite a massive set of construction in that year. We've got the University of Hawaii Educational Telescope. That's one of the old USAF telescopes. That's since been upgraded to a 0.9 meter scope, but they're still having teething pains with it and having a devil of a time getting it up. UCURT, the UK infrared telescope at 3.8 meters. As you may or may not know, UCURT is in real trouble. The UK pulled out all funding for it. The Joint Astronomy Centre is desperately trying to keep it running. It's running in an unattended mode for which it was never built. So that's not a pretty sight. University of Hawaii 2.2 meter, which is actually operable from Honolulu, as well as Hilo, and is one of the major telescopes for University of Hawaii undergrads. This little telescope here was actually removed to make room for Gemini when that went up. And the NASA Infrared Telescope facility, this is a really cool little facility. It's pretty small, but it's got some very interesting features that are keeping it useful even now. And then finally, we've got the Canada-France-Hawaii. At the time, that was a pretty respectable telescope. I just put up a little graphic here of the mirrors that you've got on Mauna Kea and tossed in these two for reference. The Hale telescope had been the unquestioned king of large aperture from 1949 right up until 1975, and nobody was going to repeat this one. The telescope was a real child of the Depression in any number of ways, not in the least of which hideously expensive to build. And it took years, not even counting the delay for the Second World War, to grind that mirror. And the mirror definitely had its problems. For example, the one that's in there now is the second mirror blank. The first one failed completely, and I can't imagine anyone being able to do that now. So when 1975, when the CFHT project started, this pretty much was, well, we're never going to go there. Partly conservatism, partly because it was hideously expensive to build these big monolithic mirrors. So the 4-meter telescope class seemed to be pretty much state-of-the-art, practical state-of-the-art. Later in 1975, the then Soviet Union announced first light for their 6-meter telescope, the Bolshoi telescope alt-azimutny, basically big alt-azimuth telescope. And it was pretty obvious pretty quickly that that thing was an absolute white elephant. The performance was horrible. The location stank. For one thing, they're in the Caucasus Mountains with very few clear days and horrible conditions at the best of times, but the mirror itself was an absolute disaster. Cracks in it filled with little bits of black cloth. In fact, later they replaced the telescope. It's still in a rotten position that they can actually use it. So this was a pretty respectable telescope at the time. And as I'll point out in a little bit later, UCURT, even by modern standards, is still a pretty respectable telescope for what it is. So now we'll move to today. Chris animated this for me so you can really see how it's changed. We have the Planetary Patrol Telescope removed to make way for Gemini. We have the Subaru telescope, the 2 Keck telescopes, and then the sub-millimeter telescopes, which I'm not going to look at. right now, since these are actually basically radio telescopes, and they actually use antennas. As a side note, James Clerk Maxwell here, that's also done through the Joint Astronomy Center, and that is also in serious trouble. The Netherlands has pulled its funding, the UK has pulled its funding, and I haven't heard distinctly on Canada, but I don't hold much hope. There's been some inclination in operations, but it's not looking good. It rather irritates me because the royal family could operate these two telescopes. It costs about $3 million a year to operate them in their minimal mode, and the royal family could pay that at a chunk change. But no, that's another story for another day. So in this big environment of huge telescopes, well, what really made the difference was a set of new technologies that was simply not available in 1975 to 1979. You can tell when you look at the dates here. I mean, it took 13 years before Keck 1 opened its doors, and part of the thing was the new technologies that made this possible were the segmented mirror and the meniscus mirror. In this case, the segmented mirror is pretty obvious. You have a whole bunch of separate mirrors, each separately controlled. The meniscus mirror is a relatively thin mirror that's capable of being actually distorted under pressure. So both of these operate on the basis that gravity is going to distort, and you're going to use a control system to undistort them. That obviously requires a relatively high-speed computer that can handle the basically, I think it's a 10 millisecond cycle to for the Keck telescopes. I wouldn't want to swear to that one, but it's certainly a pretty quick cycle, and that requires a high-speed computer system that simply was not available in 1975. So, which leads you to the question, how do they stay relevant? How does a 3.6 meter telescope, now in the age of 8 and 10 meter telescopes, by the year 2000, you're looking at 2 10 meter telescopes and another 10 meter telescope that would later open in 2007 in the Canary Islands. And at that point, 7 8.2 meter, 8 meter class telescopes. So in that environment, how does a relatively small telescope work? One of the things that helps is you've got 9 big telescopes and a few other ones that were in construction at the time. So there's still a lot of competition for the big scopes, but even so, one of the ways that they were able to do it was by taking advantage of what they had available when the telescope was built, and also taking advantage of higher technologies. For example, this humble little thing here, this is the Mauna Kea atmospheric monitor. And in addition to high-end weather instruments, this also has all sky cameras built in. That was actually built to do survey for the 30-meter telescope project, but what's happened is CFHT has taken over operation of that, and they're using that to provide weather services to the entire summit, but also for their own operations, and they look after this as well. So if you take a look inside, this is the Canada-France-Hawaii telescope. It's definitely an old school scope. You can see it's still equatorial. One of the things that the Bolshoi telescope Alt Azimuthi did, Azimuthi, because there's no did was to demonstrate, yeah, there's really no reason to stay stuck to an equatorial telescope. That was necessary when you had very simple control systems, but you don't need it anymore. But so this was one of the last generation of that telescope. And up here we've got something that was unusual for the first few very large telescopes, which was a prime focus observing cage. There's still Cassegrain instruments. There's a Coude focus available as well, but that hasn't been used for years. Actually, the Coude focus room down here is completely filled up with storage at the moment. And there's no plans to ever use it again. It's just one of those things that's not worth the trouble. So when we look at this actually adds some interesting options. I mean, this was originally built in a day when this was a manned focus cage. And you would actually climb up here and do observations. They don't have that cage anymore, but that still left a rather intriguing opportunity for them. The Keck telescopes and the Gemini telescopes do not have secondary instrumentation. They're all using Cassegrain focus. Subaru, interestingly enough, put secondary position equipment in up here. Now, I put this one in because this really gives you an example of one of the things that they've done to stay current, and that is upgrade like crazy. If you're of my ilk, of my advancing years, this will look familiar. Yeah. We have completely analog weather gauges. We've got, the little moving dial thingies. We've got annunciator switches, which I haven't seen used in decades. These are the beautiful little ones with the beautifully engraved logos and the switches inside, and they haven't been used. They're just too expensive. But they've quite neatly stitched in newer technology stuff. You see here the old technology TV monitors next to the newer computer monitors. And right up here, this little hole, I should have taken a close-up picture, but that little guy reads Mr. Photon. He's just wedged in there. Yeah, well, I guess at that altitude you start playing silly games. Now, you compare this to the Gemini Norse Control console, and this is, again, just one of them. There's not an analog piece of gear anywhere in that room. Nobody does analog much anymore. So, CFHT is upgrading, but they're doing it by bits and pieces. But it also means that they've got an upgradable system. CFHT can be operated completely from Waimea, from the town of Waimea. They can actually leave that unattended for days at a time. Gemini, well, they can do remote observing from Hilo, is still operated at the summit. And CFHT can be completely left unattended. Actually, there have been cases that I was told about where the operators and attendants from Gemini would run over to CFHT and look after some small glitch, something minor like a door sensor that showed the door was ajar when they didn't think it was, and silly things like that. Part of it too is CFHT provides services. They do all the illuminization for all the small telescopes on the summit. Naturally, they can't do it for Subaru and Gemini, and Keck has its own arrangements. But this is partly how they've managed to do it, is by staying up to date. There's actually sensors all over the place inside CFHT, including sensors on the telescope floor that will actually detect hydraulic fluid leaks. So these things are actually designed to actually place a computer call to the techs on call. So they'll actually be called at home by the instruments, basically saying, "Help, I'm broken, fix me." And they can be up on the summit in about 2.5 hours. The other thing that you can do with this, backing up a bit, is these secondary instruments are incredibly quick to change, and they've got quite a raft of them. There are 3 of them here. I couldn't get a picture of the third one. The third one is a standard secondary mirror, an f2.8, if I recall, secondary mirror, which they use for the Cassegrain instruments. But here you've got WeirCam. It's their infrared imager, a pretty respectable instrument. It's a cooled 4K by 4K imager, which gives you a field of view of about 20 arc minutes square, which is a pretty respectable field of view. And this one they use during the bright moon periods, about 10 days centered on the full moon. Over here is MegaCam, which was another CFHT developed instrument. This is a 340 megapixel imager with a field of view of 1 degree square. And that's still pretty cool. There's some bigger imagers around, but this for quite a while was one of the biggest. Sheer fluke, I managed to get a bit of correspondence with one of the CFHT instrumentation technologists. And one of the things he'd informed me was they can do a complete upper end change out in under 4 hours. So you can do a complete instrument change in under a day. You can be operating with say WeirCam one night and MegaCam the next. And that's almost unheard of up there. There's only one other observatory that can do changes that quickly, and that's the NASA infrared facility. They can do equipment changes in 15 minutes because it was built for quick change. So they actually will change in the middle of the night if the conditions go sour. It's one of the ways they've stayed relevant.
Tim,
yeah?
What's the focal ratio of that scope when it is used in prime?
In the prime focus, it's f3.3. So, it's a reasonably fast gadget. One of the advantages to having these up here is they can do changes on the Cassegrain side, because they've got some fairly sophisticated equipment down there, but you can do changes on the Cassegrain while running the prime focus imagers. So you're not taking the telescope offline to do the Cassegrain work. And again, any of the other imagers, with the exception of Subaru, and I'm really not certain how they're using that. I wasn't able to find that one out for tonight. these guys can stay on the air much longer than almost any other telescope on the mountain, and they've got tremendous flexibility for their users. So that's one of the real ways they've managed to stay current. But as you might guess from Megacam, they're also staying quite current by really pushing the edges of imaging technology. These folks are trying out stuff well in advance of any other place on the mountain, and they've got quite a technical team to work on it. Here's an example of one of their items. This is a camera called Citel. For the life of me, I can't remember the acronym. It's partially French and hammered to blazes to make a pronounceable name. But this is basically a multi-object spectroscopic camera, the guts of which were developed at Momagantic. And this is where they've actually done some of the initial testing. This is some of the stuff that was built down in the shops in Waimea, including a rather intriguing cooling system. Most of the cooling systems for most of these observatories use a total loss liquid nitrogen system. You just pour in the liquid nitrogen, it boils off at the end of the night. It works well, and it's not very expensive, but it doesn't work well with their unattended mode. So what they've done with this one is there's a small cryostat built into this that is actually refrigerating without loss. And they're getting this down to minus 100 just with the cryostat and with a temperature stability of about 0.1 degree. Here we've got Citel being tested for the first time, and this is the cryostat right here, this tiny little beast here. That's your cryostat for the whole thing. They're hoping to have this installed and running for actual big scientific work by the end of the summer, and we'll see how that one goes. Another example of upgrades is, you may have noticed, Subaru has some interesting methods for getting air in, and Gemini, I should have put a picture of Gemini up, but they've got those incredible wind vents that allow them to completely cool out the observatory. They did an interesting set of water tunnel tests for CFHT, built a little scale model of CFHT in Waimea and turned it upside down and ran water past it, and came up with the design for these vents. They're about 6 feet wide and about 40 feet tall. This one's just going in for testing back in April, and if all works out, they'll have all 12 of these installed probably by the end of the year. And again, this is all to get it chilled, get it cooled down rapidly, minimize air movement problems. They can lift the skirt up fairly high to block off the telescope as needed. So all of this is to keep the telescope operating at the best possible operating condition. The only problem is that's not going to work forever. The 30-meter telescope just got its approval from the Hawaii Bureau of Land Management. Mind you, it still has to get funded, but it's overcome some of the last hurdles, which was basically a lot of people not wanting any more development on the summit of Mauna Kea. And there's still a tremendous kerfuffle over that one. But the Mauna Kea observatories have a pretty good record of being very diplomatic with a lot of the folks like the old Hawaiian groups that are really trying to keep the cultural stuff, relevant. Whether you think that's a good idea or not is it doesn't really matter. They're there, and you have to consider them. And the Mauna Kea observatories have done a really nice job of working with these guys instead of basically telling them to go away, which I think is an intelligent thing to do. This is a monstrous freaking thing. I mean, it's 30 meters. It's big enough that you can put this thing 100 meters below the summit, and this is still not being obscured by the rest of the cinder cones up here. Apparently part of the reason for moving it or siting it down here is to keep airflow around this thing from causing local seeing issues on the summit itself. How much of that is accurate, I really don't know. That was the press blurb from the 30-meter telescope consortium. But you can see here Canada, France, Hawaii, and Gemini, and Keck down here in the sub-millimeter valley. I mean, this sucker is enormous. Just take a look at the mirror. That's 492 hexagonal segments. And even Keck looks tiny with this. And you look at CFHT, and the central opening is roughly the size of that mirror. So there's a limit to how long they're going to be able to keep operating on technology. Which led me to the question, if CFHT is running that issue, how are these little small fry going to handle it? The answer is actually kind of interesting. These telescopes here are for students. These have been completely relegated to undergrads. The 2.2 meter can actually be operated from Honolulu now, so they don't even have to come up to the summit anymore. That'll really annoy a few profs who won't be able to, injure graduate students by sending them up to freeze their tails off. Well, they still freeze their tails off in that one if they ever get it working properly again. So, how do you compete? Here's the giant Magellan telescope, which is going in Chile. 7 8.4 meter mirrors arranged in a 27 meter array. 2 of these mirrors are complete, and there's at least 2 more in the pipeline. So this is happening relatively soon. The European Extremely Large Telescope, the last press release I got from that showed a 39 meter mirror. I saw an earlier one that said 42, but I'll take the most recent one that they listed. And again, that's got complete approval. They've even blasted the top off the mountain where they're putting that in. This sucker is happening unless something incredible happens. And a lot of countries have poured support into this. So how do these little small fries handle? Something I discovered, and I would love if somebody could give me an explanation as to why, infrared telescopes, the pure infrared telescopes, just aren't very big. This is VISTA. And despite the name, Visual Infrared Survey Telescope for Astronomy. And I mean, obviously, they botched that together to make it pronounceable. It may say visible, but this sucker is optimized purely for infrared. They don't do any visible work with that. That's the world's largest right now, at 4.1 meters. So in that, you can see UCURT at 3.8 is still quite relevant. Interestingly enough, South Korea has expressed interest in buying UCURT, which has led a few of the wags up there to note that it would now be skirt. Yeah, the guy who took me through CFHT had mentioned that one. He was not happy with the whole concept of letting this thing be destroyed. Basically what happens with telescopes as they become inactive on Mauna Kea, the University of Hawaii gets first crack at the telescope if you want to get rid of it. They have to be offered first opportunity to buy it. If they don't want it, then it can be sold to an acceptable user, and University of Hawaii gets last call on whether or not the user is acceptable. And if that doesn't work, the telescope has to be removed in its entirety and the site returned to the original pristine condition. And the estimates for that for UCURT are sitting at about 15 million to do that. I point out it costs about $2 million a year to operate minimum mode. So it would cost them about, 7 years of operation to take the thing out. So who knows? And then the NASA infrared telescope, a bit small, but the incredible flexibility with that thing makes it still an incredibly valuable scope. And again, this tends to be used a lot now by undergrads. So again, this is staying quite relevant for a while. So with that happening, the only real thing is to look at removing and upgrading the telescope. This is the latest proposal to come out of the next generation CFHT workshop that was finished just this April. They're looking at a 10-meter segmented mirror, this Colot-style dome, which seems to be really quite in nowadays. I'm still not entirely sure how this geometry can work, but this whole thing slides up and down like an eyeball. I'm not sure where you put the rest of it in here, unless it rotates in some strange way, but that's how it goes.
The way I understand it.
Yeah.
This part rotates.
Yeah,
like this,
rotates around.
You get the altitude,
Yeah.
the aperture changing.
That's how I get it. It's going to be a devil of a control system issue, but what they're planning on doing is using the existing lower building and the existing pier, and they just did some surveys on it last summer to demonstrate that the pier is actually capable for handling about 5 times the weight of the existing telescope. So it can handle the weight of, I think, about twice their planned 10-meter telescope. Again, the killer with this one will be funding. And funding is going to be a big issue. Taiwan and South Korea have indicated significant interest in backing this. Actually, South Korea already has some arrangements with CFHT for use of instruments in time, and they've done some development on instrument work. So perhaps they will be able to save it. But basically, they're hoping to have this by the end of the decade. Again, and I think the whole thing is going to come down to funding. Certainly France is not in great condition, neither is Canada. And for the United States, well, we've seen what sequestration has done, and I don't think that's going to get better anytime soon. Chris commented on this one. I added this at the last minute. His comment was, well, yes, of course, every presentation needs a nice sunset. I could give you some kind of nonsense about how, yes, you know, the sunset of the Canada. Well, actually, I put this in for only one reason. I really, really, really like the picture. It's real pretty. So that's why it's there. It has absolutely no purpose whatsoever but sheer utter sentimentality. So there you have it, folks. That's my take of CFHT. I remind you, I am no expert. I learned a lot by listening to the operators there and then did a fair bit of research. I'm as up to mistakes for this as anybody, so if anybody's got anything to share, I'm really fascinated in this. How you keep telescopes working, to my mind, as an engineer, is kind of just as much fun as the science that you get out of it. I think it's incredible operating these things. So, you know, if anybody's got some suggestions or some information or some insight, I'm all ears. Okay? Thanks very much for not falling asleep and snoring. Have a good one.
I'm going to move right along to our observation reports, and we have some good ones for you tonight. We've got quite an interesting collection. First up is Paul Shepard.
Not here.
He's not here? Oh, okay. I guess we'll show it for him. Obviously, Paul caught this rather nice image of the conjunction of the three planets, Mercury and Venus and Jupiter, not too long ago. I also tried to get this from my neck of the woods and got nothing but clouds for the 3 days where it was at its best there. So yeah, nice shot from Paul Shepard. All right. Moving right along. John, I know you're here.
Paul, can I do something about the light on the podium, please?
Yes, we can.
There's a
Thumb switch. Is there? Oh, okay. There, just turn it off. Do we have a cable underneath here or anything? We're okay. There you go, John.
Oh, thanks.
It's the one on the, yeah.
Big one. Yep. Is that the slide or the? Is there?
Or you can just ask Chris to advance it.
Is there like a laser pointer?
In the center bottom.
This one. Oh, yes. Okay, so the three photos that I'm going to show you are.
You got to speak into the mic.
Yes, the three photos I'm going to show you are. They were taken May 4th. I was lucky enough to be over at Paul Cloninger's house, and he's got a fairly dark sky there. Now you all know where to go. Sorry?
Speak up a tad, please.
Sure. So this photo was taken, well, they were all taken with my digital SLR camera with, well, this one was taken with a fisheye lens, 8mm. And it's kind of faint in here, but you can see a meteor trail in here. And that's Paul, busy setting up his telescope. Let's see what else I can say. Oh, it was...
Is that Saturn?
Yep, he was just circling Saturn.
That's right. So you got Spike over here, and that's Saturn. So you got that.
Yes, and we had Glenn LeDrew was there as well, and if it wasn't for Glenn, my next two shots wouldn't have been possible because I couldn't find Comet pan stars on my own, but Glenn knew exactly where it was at any point in time during the night. Okay, next slide, please. So that's a composite of three images. They're each 1 minute in exposure, 200mm lens, f3.2, and ISO of 6,800. The interesting thing about this image is that the comet has kind of like two tails. Well, it looks like two tails, but it's actually just like a big flare, a wide flare. Okay, and the next image, please. This is with the 400mm lens, and it's also 1 minute exposure, but it's 7 images put together into one composite.
Could I explain something about the image? Is that okay?
Oh yeah, go ahead.
when we're looking at the comet here, the Earth is approaching the plane of the comet's orbit, where we're going to cross through the plane and see all of the dust tail, which is in a great big huge arc along the line of sight, edge on to us. So the plane, if you could imagine, if I put a big sheet of paper from here running into the screen at an angle and going beyond the screen into the distance toward the left, that would be the plane of the comet's orbit. And as we're traveling through space, we're moving toward the right, so that in successive days, this great big huge fan of a tail with the primary up and the secondary down will become more and more straight and straight, until just recently when we passed through the plane, when all of this was just a needle straight line in the sky. And then of course as we continue beyond, we'll see an inverse where now the tails will do a fan becoming more like a reverse image now onto the right side. So just to get a picture of the geometry. So we're just looking at this huge fan of a curving tail extending into space, mostly away from us, but from a little bit of a perspective to the left, our line of sight, seeing it from one side.
Why the split tail?
It's not a split tail, it's one continuous tail. It's just a great big curve, because as the orbit of the comet carries it around the sun, its changing velocity vector means that the dust that's ejected at different times, as it's going around the sharp curve circling the sun, it forms this great big arc in space. So if we could see it from sideways, from say way over here, this way, the tail would be a huge curving arc with a great big fan with probably different synchrones. So you can see the tail, which are indicative of the alignments at different periods of the dust at different discrete points along the line of in the plane of the orbit. So that's really it. So it's not two tails, it's just one. And the other thing is that as we get closer and closer to looking nice and edge on into the plane of the orbit, the surface brightness of the dust tail increases because it's a fairly thin sheet. And we're just looking at it through kind of a sideways perspective, so the optical depth is not as great, but as we get closer and closer, moving through space and then see it edge on, then it becomes a nice sharp, fairly high surface brightness needle-like line for a short period.
Glenn, what's the date for edge on this?
Paul,
27th of May. We passed it already, but it's still pretty edge on. It's still pretty. I've got a shot later that'll show you just from a few from last week, where it was close to that alignment date there. But it's still pretty. It's still pretty linear. It's starting to fan out a little bit toward, as Glenn said, to the other side now.
Okay, the only other thing I wanted to mention is that I was using my barn door tracker with the camera to get the 1 minute exposures.
Awesome. Thank you.
Okay, thank you.
Yeah, if you didn't mention that, I was going to mention that, because that's pretty impressive off a barn door tracker. I mentioned that to John when he was out at my place doing that night. I was quite inspired by what he was doing there. 400 millimeters, I think the best I've ever done off a barn door is about 135, so nice piece of work there, John.
Is that motorized?
Yeah, motorized and then some. Yeah, it's not your simple twisty, that's for sure. All right, up next, Gordon. There you go, sir. There's the remote.
Can't see. This is the remote? No?
No, that one right there.
This is the remote. Okay. Well, I can't see my notes, so I'm just going to wing it. M59, M60, and M4. Okay. Can't read my notes, so I'm just going to wing it. M59, M60, and NGC 4638 in Virgo with my 12-inch scope at 115 times magnification. It was just a nice little trio and a faint little galaxy up there. My challenge, if I ever get out of Orleans to do some observing, there's another galaxy right here that I want to find, and there's supposed to be another one, I think, right there. But they're a little too faint for Orleans. Next, please. M106. And its companion, again with the 12-inch, 187 times. Next, please. A meteorite through the Big Dipper, Ursa Major. That was naked eye observation just a couple nights ago. And this next one is Saturn. I talk a lot about sketching, and I'm trying to encourage people to do sketching. Don't be intimidated. You can see I didn't really do much with Saturn there. It's just a smudge to get the approximate size and shape. I've cleaned the sketch up with in the computer just to make my stars and moons round. And the next one, I've got the labels for the moons that we're showing. And again, if I could get out of Orleans, there's another moon showing here, and a little tiny one down there. And the only other thing I have is last month Estelle had recommended a book, which was the 4% Solution. No, sorry, the 4% Universe. It's by Richard Panik. And I think that must be a pen name for Dan Brown, because this thing just reads like the Da Vinci Code. I mean, it's just a real page turner, if you can believe it. And it's talking about dark matter. He doesn't tell you what dark matter is, just that it's dark, but it doesn't really matter. It's a great read. Thanks.
All right, Rick. Rick's got some cool stuff for us. He's been drinking more.
Okay, so yeah, so I started diversifying my observing a bit and gone, in this case, I don't know how most of you were probably here last month, but gone retro. So we're back to chemical-based sensors like film type stuff, ISO 4, camera that's f140. So we make that up for that by using a 7 million second exposure with the Jamaican red stripe camera. So that's basically a view of my house, and what we're seeing is the trail of the sun going overhead every day for about 3 or 4 months. And you.
The house reminds us how you got the picture.
What's that? Yes, that's right. Well, you don't get a whole lot of resolution out of these beer can cameras. Yeah, I know. So you can see the gaps. Gives you an idea of how good a year it was, how good a spring it was for the amount of sunshine we had. Next. This is one I had the camera oriented horizontally, and so it gives you a different perspective. This is facing probably slightly east of south, and so it gives you a different distortion on the trails of the sun, and you can see the trees as well get quite a bit distorted. And next, this is another one. If you remember last time I talked, one of the ones from the waterfront at my place, and it's got these 3 big, looks like brick marks running up and drops up there as well.
Finish the beer next time.
Yeah, that's right. So this was the same can on the same tree in the same location, and it's giving me the same problem. So I'm thinking maybe it's the can, so I'm going to try a different can, which of course requires more beer.
Are you sure this wasn't Rickard's red?
This is, yeah. So the other thing, of course, is this will come up again later. These are actually star trails, right? But anyway, so you see the view here. This is out over the dock and the islands in the distance. Next is, this is a view at night with an actual camera. This is a panorama around basically from dead east to dead west. You can see Kingston on the far right. To the south, I think, is Gananoque, and to the left, I'm not even sure. It might be Brockville, but I'm not sure. What's particularly interesting about Kingston right now is Kingston City has just embarked on replacing all their street lighting with LEDs. So over the coming year, I expect the intensity and the color of the light to change. So there's a group of us from the Kingston Center who are trying to take pictures under exactly the same conditions, like same camera, settings, et cetera, right on a fairly regular basis throughout the year, so that we'll be able to track the change in brightness and color. Next. Oh, well, you can see it was an ISS pass. I got my green laser out and labeled it in case I forgot. So again, star trails. This is just DSLR mounted on a tripod, set to do continuous 30-second exposures for about 15 minutes. And this was quite a nice pass, fairly bright, going fairly high over the North Star. And unfortunately, a couple of airplanes got in the field as well to confuse things. You can see actually the space station moves fast enough that in the about half second between exposures, there's actually a little break in its trail. Next. The Lunar X, also known as the Werner X. Do we have a pointer?
It's on the
there we go.
in the center of the middle button.
Middle button. Ooh, nope, that wasn't. I can't see any buttons here.
Big thing in the middle.
Oh, okay.
That's the Bolson X, isn't it?
I hope not. Yeah, so these are the craters Werner, Aliacensis, Appianus. I don't know if you know, but in a lot of cases on the moon, if there's a fairly significant crater, it has a name, then surrounding smaller craters are labeled A, B, C, associated with that one. This is one where the crater Playfair has Playfair G next to it, which is, so it's kind of backwards. But anyway, so this feature is just an intersection of terrain between a bunch of craters. It appears for about 4 hours near the first quarter moon. So most of the time during that 4 hours, it's, the moon's too low in the sky, or it's not up in the sky, or whatever, or it's daylight. And so it's not a terribly easy thing to spot. However, the observer's calendar does have them marked. And so if you look in there and check carefully like I did every month, you'll find that the next time it's visible from our neighborhood is the 9th of December. And it's quite interesting to watch because it really does just appear over a period of about an hour, hour and a half. It goes from complete black to this X appearing, and then gradually the terrain around it lightens up and it begins to disappear. I realize this isn't a great image, but it shows you what you can do. This was an 80mm refractor mounted on a tripod, so it's not even driven, just with doing a short 640 by 480 video with the DSLR, and then stacked in one of the many stacking programs, and so it still comes out fairly respectably. Next. Another thing I've been doing recently is some solar H-alpha imaging. A friend of mine has loaned me his 60mm Coronado filter. So I was having problems getting focus, so I went out and bought a new DSLR that has live view on it, so now I can actually focus the images better, and so I'm getting some more improved results. So this is from the 6th of May. What we're looking at is a couple of sunspot groups, and then these are filaments, which are actually prominences seen against the disk. So they're actually cooler areas that are absorbing the light coming from the disk. And then, of course, on the limb, they're visible as little protrusions. And next. And this is from the 9th of May. You can see the big spot group has moved over towards the limb there. And a particularly nice prominence there. There was a really nice waterfall prominence back a couple of weeks ago. Great huge thing, as tall as this one and about that wide. But unfortunately I didn't get any images. It was only clear for a very brief period and didn't get anything that day. Next. Okay, so this is some barn door tracker images. This is a 100mm f2.8 lens, stopped down to f4 on the 60DA, Canon 60DA. Corona Borealis. I think it's a really pretty constellation. The diffraction from the aperture on this lens actually puffs up the brightest stars enough that it really shows the constellation quite nicely. There's not a great deal that's very exciting in Corona Borealis, except that there is R Corona Borealis, which is, I think this guy. That's a star, and actually what's interesting is you see these three stars, they're all about the same brightness, so they're all around 11th magnitude. Our Corona Borealis is normally around 6th or 7th magnitude, except that every so often it puffs off a cloud of carbon, which condenses to form dust, which obscures the star for a few months, and then as that cloud expands and stuff and gets more tenuous and stuff, the star returns to its normal brightness. So what you can see actually is it means in this case I've actually caught it on its way down in brightness. And the other star is this one, is T Corona Borealis, which is kind of the opposite feature. It's one that suddenly brightens up enormously. It's actually a recurrent nova, so it's a white dwarf that's sucking material off another star, and that material builds up and builds up on its surface until it suddenly ignites, and the thing comes up in brightness by 6, 8, 10 magnitudes and becomes quite a bright object in the sky. It's done that twice in 1866 and 1946. So if that's a regular period, we should be expecting another one in about 2026, so keep your eyes open. Next. This is Melotte 111. It's one of it's the sort of the main star cluster in Coma Berenices. Don't normally think of the star cluster itself. You always hear about the Coma Virgo group of galaxies, but you can see NGC 4565 as a nice little spindle there. What's really neat is if you've looked at the galaxy, you actually know there's a 14th magnitude star just off the side of it. It's actually visible on this image. And losing my notes. It's kind of blurry here, but there's I don't know. Anyway, another galaxy in here. There's several galaxies visible. Oh, thanks. Several galaxies visible in that field. Next.
Goes the beer.
Yeah, no. Oh, thank goodness it was empty. It was
the other galaxy we're looking at is right here.
There's that one. There's another one down. Oh, here we are. Here's another one. If you look carefully, there's lots of them. I guess. Do I have control? No. Okay. Next. The bowl of Ursa Major. So there it is. There. What's neat here is you can actually see M108. And a nice little greenish planetary nebula, the Owl, M97. And then M109 is another galaxy over here. Now, many of you will know that this is an area that's got lots of galaxies in there, so there should be more than that. So I went over this one carefully, looking for all the non-stellar objects, and I marked all of those. And then I went through with a star atlas and marked all the ones that are visible in here but not noticeable as galaxies. And if we go to the next picture, there they are. That's what I've picked up with a 100mm lens. So the yellow ones are the ones that are obviously detectable as galaxies. The red ones are all basically stellar, but look stellar on the image. Next. This is the handle of Ursa Major. You can see Alcor and Mizar down here, and then the tip of the handle, and M101, big spiral galaxy up there, and M51 down here with its companion. So those were all with the barn door tracker. I think they were individual exposures were 1.5 minutes, and they're generally about 10 exposures each combined. Next, so now I've moved up to 405mm focal length, 90mm apo refractor on an equatorial mount, and M101, a little more close-up view. You can see the nice spiral arm structure and a couple of galaxy. It's got a bunch of companions. This one's particularly interesting because it's actually a very irregular kind of spiral where and they think it's because of distortion from a passage by M101, but its nucleus is actually way off to the side. It's not nearly in the center of its spiral arms anymore. Next, and M51. Again, you can see spiral structure in the main galaxy and its little companion with the arm connecting the two. And then, as we saw in Bob Olson's picture earlier, the three little tails that stick up, and then another one that comes out the side there. And those are tidal tails, of course, from distortion because of the interaction. And then again, there's several other galaxies in the field along with it. Next. Gamma Cygni. So this is the center of the Cygnus Cross, the bright star there. And the nebulosity is all IC 1318, hydrogen alpha emission nebulae. And you can see the variation, all the number of stars in some area, and then other areas are quite sparse in stars. And that, of course, is because of dark gas and clouds that are obscuring the stars behind it. And of course, this is almost right on the plane of the Milky Way, so of course there's a lot of open clusters. The most obvious one here is NGC 6910.
It's worth noting that it's noticeably yellowish because of interstellar reddening.
Yes. Yeah, a lot of the stars in that area will be reddened by the dust. It's an interesting thing. Back around the late 1800s, I think it was, there was a big discussion about these darker areas in the sky, and are they actually holes where there are no stars, or are they clouds that are obscuring the stars? And one of the neat presentations that I heard about was somebody's suggestion was, if it's a hole with no stars, that hole has to continue in a straight line radial from us for a great distance of no stars in order for there to be no stars visible in that spot, whereas a cloud just has to be a lump in the foreground. And that was one of the concluding arguments. Anyway, there's a bunch of other supposed clusters in here. I might almost say imaginary clusters. I think this is a colander cluster. There's another colander here, a Vandenberg, a Rosalind, I think, maybe. I can't remember who else has clusters in the area, but there seems to be guys out there who collect these things. Men after Glenn Ledrue's heart, I think. Next. Oh, Comet Pan-STARRS. So this is from just 2 or 3 nights ago. And this would have been basically when we were almost looking straight down the plane of the tail. So you can see it's still extending out a bit on the left-hand side and almost looking double. This is about 12 or 14 5-minute exposures. And basically what I did was I took them all, I aligned them all on the stars, so in case there was any rotational change in the pictures. So now I've got them all aligned straight, and then I shifted them all to the nucleus of the comet so that it trails all the stars. Next. Oh, a little bit of star trail stuff. So you take your camera, you stick it on a tripod, and in this case I pointed it off to the east and took a 30-second exposure, and you get a nice picture of the stars. I think this was at ISO 1600 and f4 with a 10mm lens. So lock your shutter release and you take a whole bunch. What I did was I just went away and observed from 11:30 till about 3:30 and came back and turned it off at that point. And you end up with 500 pictures very similar to this, all slightly different positions. So you can add them all together. Next. Oh no, first, yes, you connect them all together in Virtual Dub or some such software, and you can get a video that shows the Milky Way rising in the east, and airplanes going through, of course. You can see the dark horse down here. So that Scutum star cloud there, M24, Sagittarius star cloud. So that's cool. Oh, there's twilight. I guess that's why I stopped observing. So if we then take all of these and put them into a script, or what they call an action in Photoshop, you can add them all together and get next star trails. And what's interesting then is it makes it easy to see that there were actually two interesting objects, hoping they are meteors, but they aren't actually. I went back and checked, and sure enough, you can actually see that this one is broken in two places, so it took over 30 seconds. This one was actually broken in one place, so it took about 30 seconds as well to pass. So they're both satellites, presumably. This one I was actually able to go to heavens above and find that, yes, indeed, at exactly the right moment, there was an iridium flare. Not the right one. This one I'm not able to go there. But anyway, I think it's a very pretty image. Something I like about it is that it shows up the color of the stars a lot. This is very well. Now, if we can add them all together, you can also make the script save, add a picture to save, add another one to save, add another, and then new movie, which is next. And what's neat here too is with the wide-angle lens, you can see, as we know, the stars all go around the pole star. But of course, they also go around the south pole. So you're getting both curves with this much of a wide-angle lens. I think it's been done before. And again, twilight. Now the next step you can do is, instead of add the image and keep saving, is you add it and fade the previous ones. And what happens is then the trails all turn into little comets. And what I like about this, for instance, is the airplanes appear and then fade out, as do the satellites, of course.
Simulating the view after you've emptied your red
cans
for your...
That's right. Spent a lot of time on your hands, eh, Rick?
I'm retired. This is all I do now. Well,
how long did it take to put something like that together?
Well, once you know how to do the script and stuff, it's 5 minutes work. And 4 hours of exposures. So, any questions? That's it.
Mr. Boyle, there we go.
Thank you. Okay, so we have some few shots here. Just waited for my wife shopping. I was in the car, just happened to notice a solar halo and just a plane passing by. Just this picture was taken with my iPhone. The projector doesn't show as sharp as it should be, so I was very surprised how well that came out. Next slide, please. Being in the country, of course, now I get some pretty neat lightning shots. Pretty hard to do in the city. People are wondering, do I have a lightning bolt detector? But easily in the country, all you do is set your ISO to 200 on a tripod, stay inside, and just keep holding down the shutter open until something flashes. I've kept it open for about a minute with nothing flashing, nothing really registered on. So they're quite simple in the country, quite simple. Now down here is...
As it is, we could call this God's cardiogram.
Yeah, it could be, could be. And then after I change my underwear, this is actually a cornfield out here, which you don't see in this shot, but next shot you'll see it. Yeah, that was kind of close. That was only about a kilometer away. The house really shook on that one. And there's the cornfield. Yeah. Next shot. Everybody has to get the plane in front of the moon, and I was just the right place at the right time. So I was pretty happy with that one. I noticed the jet coming from here. So that's interesting. Very interesting. Very interesting. And then I start shooting like crazy. And next. The beginning of May, the 2-4 weekend, again, nothing great, no big auroras as yet, just a little bit of spiking, but I'm sure we're going to get the big storm. There was one last night, of course we were clouded at KP 7. It was even seen down to Kansas. So hopefully Sunday is supposed to be good weather, maybe Saturday night, so keep watching the skies, and of course spaceweather.com. Next slide. And the trio of planets, Jupiter, Venus, and Mercury.
That's it.
And that is it. Thank you.
Thank you. All right, I've just got a few for you, and obviously we're going to be leaving our ISS video for next month, since we're already running over. But wanted to show you this one. This I shot the same night that John was over at my place there. I was inspired by what he did there, so I had been doing some imaging up in the Virgo cluster, which I'll show you in a moment. But also turned it to Comet Pan-STARRS there. So this is 1,000 millimeter focal length, and that's more of a visual appearance there. But I also did a little bit of more extreme processing to show the extent of that dust tail, or that dust fan, I should call it. So as Glenn was mentioning, that's we're seeing that still at the plane at an angle to the plane of the dust fan. That was taken May the 5th. And then just last week, I used my barn door tracker with a 50 millimeter lens to get that. So you can see that's pretty much edge on there to the dust plane itself, and what you're seeing there is just the long streak of it. This was up. This is Polaris actually, so it was up really close to the North Celestial Pole, and you could basically have shot this without doing any tracking, anything special at all. Just a camera on a tripod would have done it. That's just a 50 millimeter lens at f1.8. Interesting also on this shot, you can see the very red star there, Carbon Star S Cepheid, which happened to get in that field. So yeah, Comet Pan-STARRS is still putting on a good show even after all these months. So it's still.
Tail length, Paul?
Pardon me?
The tail length is shown here.
Oh, the tail length is about 6 degrees, so about 12 times the diameter of the full moon. Quite a large anti-tail as these things go, unusually large, and should still be visible for a time yet there. So if the clouds ever clear, we're in a moonless window. It's still hanging up around near the bowl of the Little Dipper.
Well, one other thing we could mention, because right here we're essentially passing through the orbital plane of the comet, the dust tail, which we call the anti-tail, is pointing precisely down to the sun.
That's right.
About 25 or so degrees
that way. Yep. Interesting. I've never seen one like that before. I've seen anti-tails on comets, but never one quite like that. So yeah, continues to put on a good show for us. All right. So that same night that John and Glenn were at, I was also doing some imaging up on the Virgo cluster. I've been wanting to get a shot of this. This is a M87. This is a really interesting galaxy because it's a supergiant elliptical in the heart of the Virgo cluster, and it's one of the largest galaxies in our local portion of the universe here. It's just a massive, massive beast. And at the center of this galaxy, there's nothing small about this galaxy. At the center of this galaxy is a supermassive black hole, which has an estimated mass of about 6.6 billion solar masses. So think about that, 6.6 billion suns squeezed into a singularity less than the size of an atom. Now they figured that the black hole zone, the Schwarzschild radius around this, is about the same diameter as Pluto's orbit. So yeah, if you're flying in anywhere near that area there in your starship there, you've got something about the size of our solar system that you really don't want to enter. I don't know if there's any signs around it. Anyway, one of the cool things about this galaxy is that associated with that black hole is a high velocity, very high velocity jet of material that's being sprayed out. And you can see it there. It's, that near relativistic jet of material that's being blasted out from the vicinity of the black hole. This is a very short series of exposures. It's really easy to overexpose this galaxy and lose that jet. So this is more sort of the inner portion of that galaxy, and this is just a stack of 6 90-second images to bring out that jet. So M87, very interesting beast. So also imaging in the, as I said, in the Virgo cluster there is our, this is M84 and M86, our two guys there. This is the Virgo cluster. It's part of the Virgo supercluster. The Virgo cluster itself is estimated to contain something like 1,300, by some estimates even 2,000 galaxies. And even in this image, which was actually still relatively short, this is only a stack of 6 5-minute exposures. You can see a number, you can see a couple of Messiers here, and you can see about a dozen or so NGCs and ICs. I don't know how well it'll show up with this projector system, but I also had, like Rick, I had a deeper look at this to match it up with the star catalogs and that, and there's a whole raft of lesser galaxies from the PGC catalog, so I've essentially circled them. And you can see all together in this image, there's about 5 dozen galaxies just in this one field there. So a very rich area to look at, very interesting to peruse. All right.
6 times 5 minutes.
About 30 minutes in total.
The telescope or for the lens?
No, that's a telescope. It's a 1,000 millimeter f5.3 Maksutov Newtonian with a CCD camera on it.
And the field of view here would be what?
It's
a degree or so?
It's about a degree on the short side and about 1.3 on this. So yeah. So a beautiful area there, and I love the smiley face there. He's that's always an interesting one. All right. This one now. This is not Rolf Meyer grade, but the reason I threw this in is that. Yay, I finally got my observatory working up less than a week ago, and this is one of the first shots that I took from it. It was a crummy night. The seeing was really garbage, but I just had to throw it in because it's kind of first light from the permanently mounted observatory. So I've only waited about 20 years for that. So hopefully I'll get a bit better grade as we go along. And the last one I have for you there is that guy, NGC 4236. This is a galaxy, a Bard spiral in Draco. Very low surface brightness. It's actually quite a dim galaxy. This exposure was close to an hour, and still fairly faint on the peripheries there. But interesting nevertheless. It was a good night, nice and clear out there. So that's all I've got for. I think that's the last one I have for you. Yes, on this night there, and just to wrap things up there. Yeah, we're not going to do that one because we're already running way over. Oh. Sorry. So I'm going to show that next month in conjunction, or I'll show at least part of it in conjunction with a summary of what Chris Hadfield was up to when he did his stint up there. Okay, just to close things off, we've got Estelle's pick of the month, Chasing Hubble's Shadows, Search for Galaxies at the Edge of Time. That sounds like a good read. And our usual notations. Yes. Is our art man here tonight? Okay, I didn't actually see him out there.
Coffee's just outside this door, not in the main lobby.
There we go. And again, if you want to join us over at Kelsey's there, we have our usual reservations, and also see Art for any issues regarding membership or cards. That's about it. Hope to see you next month there. We'll be back in as far as I know, we'll be back in our regular venue. And hope you have a great month, clear skies, and we'll see you all soon. Take care. Whoa, whoa, whoa. Oh, yes, we're going to slip in.
Go ahead.
Yeah, we're gonna talk about this just for a moment here, because I know some of you weren't here last month when we talked about this. As you know, the museum is starting to charge parking fees. Yeah, we're all big fans here. Anyway, that it is what it is, and we're trying to work our way around it. But in the meantime, there is some free parking available nearby if you haven't already noticed. This is the street, just to get your orientation. There's Saint Laurent there, and this our Timmy's is over here. And so the museum is here, the Rocket's here. That street, what's the name of that street? Gladwin. So that's all free parking. You're allowed to park along there. Not along this one here, Lancaster. They'll get you a ticket there. Do we have our other tips and hints? That's it, eh? Okay, so if you want to avoid the parking charge, you can try along Gladwin there. All right. Had 100 or so in our audience tonight. It was a good turnout, actually. And thanks again for all the folks that contributed images and their time to put together presentations, and the museum for our venue. Thank you very much. And we'll see you next month, July the 5th.
Thank you.